Okay, so in this chapter, we're going to be looking at thermochemistry, which concerns the energy exchanged when a reaction or physical change occurs. So let's talk a little bit about the fundamentals of this chapter, starting with this idea of energy. So energy can be best defined as the ability to do work, so essentially move mass over a distance against an external force, or transfer heat. So there are two types of energy, kinetic energy and potential energy. So kinetic energy can be thought of as the energy of motion. So for example, an object moving with a velocity v has kinetic energy, based on, well, how big is this particle? What is its velocity? So essentially, how big is your object and how fast is it moving? That determines the amount of kinetic energy that your object has. Potential energy is the stored energy in matter. Potential energy can be thought of as energy due to position or composition. So an example that's pretty tangible is that if you have a rock, so if you have a rock sitting on a really, really tall building, this rock has potential energy due to its position. Another example of potential energy would be if you have a stick of dynamite, for example. So suppose it's like a stick of dynamite. That stick of dynamite has potential energy as the result of its composition. If we light that stick of dynamite, we can use it to move things or generate heat. Just like if we have this boulder, we can convert and we can use this potential energy to, for example, cause the boulder to fall to the ground if we push it. Now, internal energy is the sum of the kinetic and potential energy for each particle in a system. So E is equal to kinetic energy plus potential energy, which we can write as E is equal to KE for kinetic energy plus PE for potential energy. Okay, so we're slowly talking about the different types of energy at play. And now let's talk in detail about each of these types of energy, kinetic and potential. For those who have taken one of the first or second physics courses, this may look really familiar to a lot of you. If not, we're still building from the fundamentals, so don't worry. So first, let's talk about kinetic energy. Kinetic energy is described as the energy of motion. So kinetic energy can be described mathematically for a particle as 1/2 mv squared, where m is the particle's mass and v is the average velocity. And we don't see it in the equation, but this kinetic energy is related to the temperature T. So anytime you see the word or the letter symbol T in these next few sections, it's referring to the temperature. So kinetic energy is proportional to the temperature in units of kelvins. Would anyone like to take a guess? Why kelvins? What's so special about the units of kelvins? What's so special about the units of kelvins? What makes it useful as a temperature scale? What's the key feature? Yep, exactly right. The temperature in kelvins is an absolute scale. And as a result, you won't ever observe negative temperature values. And as a result, You won't ever observe negative kinetic energy expressions. Very good, very good. Okay, so in takeaway, samples of matter at higher temperatures have a greater kinetic energy and a greater amount of molecular motion. So if we look at a low temperature sample, let's suppose we're looking at 273 Kelvin, which is about 0 degrees Celsius. And we're trying to look and we're trying to see, well, how is this gas behaving? So each of these particles are just moving about in random directions, and we'll write their velocity as this v here. So we'll draw an arrow to represent the velocity. So there's a relatively small amount of molecular motion. If we increase our temperature and we look at a higher temperature sample, so at high temperatures, so let's do like 373 Kelvin, which is 100 degrees Celsius. Based on what we've discussed just moments before, would we expect the velocities, the amount of molecular motion to be greater or smaller at higher temperatures? Would we expect our amount of molecular motion to be larger or smaller? Larger, yep. So we'll draw it with a larger arrow. So then, the kinetic energy at low temperatures is less than the kinetic energy at high temperatures. Okay, so when you think high temperatures, I want you to think more molecular motion. Okay, so now that we have this relationship and we're starting to understand a little bit about what kinetic energy is, it's the amount of energy that a particle has based on its mass and its velocity. And the amount of molecular motion and the average particle velocity depends on the temperature. Okay. So let's try to look at this micro scale perspective in a little bit more detail. So first and foremost, samples of matter at a higher temperature, so let's use a different color for that. Samples of matter at higher temperatures have a greater kinetic energy and a greater amount of molecular motion than samples at lower temperatures. Now, energy can be transferred by collisions between moving particles. So for example, if we have a particle moving with velocity v, and we have another particle moving with a slightly smaller velocity that we'll just call v. So let's pretend, just for this exercise, the particle on the left is from a high temperature sample, and the particle on the right is from a low temperature sample. When these two particles collide, so let's look at the next frame in this frame by frame analysis. The two particles will collide, and when that happens, there is a transfer of kinetic energy from the high kinetic energy to low kinetic energy particle. So at the end of this collision, what immediately is apparent is when we look at our two particles again, now our high temperature particle has a lower velocity and our low temperature particle has a slightly higher velocity. So then, as we can see from this picture, our high temperature particle lost energy, it lost kinetic energy, and our low temperature particle gained energy. Does this idea make sense to everyone? So particles can collide. When they collide, there's a transfer of kinetic energy. And then when the particles complete their collision, the high energy particle lost some of its energy, and the low energy particle gained a small amount of energy. Does this idea make sense to everyone? That when particles are in contact, they can transfer some of their kinetic energy, or in general, just transfer some of their energy? Can I get some responses in the chat just to make sure that this idea makes sense to everyone? Any questions on this concept? Okay, perfect. So based on this idea, objects in contact with each other will transfer energy until they reach the same temperature. We call this process, we call the state when both objects are at the same temperature, thermal equilibrium. It's just a fancy way of saying the objects are at the same temperature. The net exchange of energy between the two objects is at a net zero. So now collisions of fast particles with slower particles causes the slow particles to speed up while the fast particles slow down as energy is transferred from the faster moving particle to the slower moving particle. So for example, in this picture, just like in our micro scale depiction, we have a high temperature sample with a large kinetic energy. Why was I able to immediately assign the box on the left as our high temperature sample initially? What is so special about this sample? What's my key indicator? What's true about the high temperature sample? Do we see a depiction of a large or small velocity for this high temperature sample? Do we see a depiction of a large or small velocity? Yep, a large velocity, right? We see these large arrows indicating a large amount of molecular motion. So we have our low temperature sample with a relatively small kinetic energy. The particles are allowed to collide. So we can say, in effect, that there is a transfer of energy. So there is energy is transferred from high temperature sample to low temperature sample. And then eventually at the end of this process, both samples are at the same temperature. Does this idea make sense to everyone? So really, transfer of energy between objects is based on particle-to-particle collisions, fundamentally. A high temperature object, the particles have more energy, so when they collide with the particles with less energy, they transfer some of their kinetic energy. This in turn results in a change in temperature of both of our samples until they reach thermal equilibrium, until they reach the same temperature. So just to drive down this point, as the high temperature sample loses energy, the sample decreases in temperature and the sample loses kinetic energy. As the low temperature sample gains energy, the sample increases in temperature and the sample's kinetic energy overall increases. The transfer of energy between objects results in the change in temperature and molecular kinetic energy of each object. And we call the energy transferred from a high temperature object to a low temperature object the heat or thermal energy transferred between objects. And we're going to be focusing in on this idea of heat throughout this chapter. So Let's talk next about potential energy. Potential energy is the energy due to position or composition. So one key situation that we're looking at for potential energy is that potential energy increases when objects that attract are moved apart and objects that repel are moved closer together. Now, potential energy can be best thought of as stored energy that can be converted to kinetic energy or heat. So one classic example of potential energy is this idea of a spring. We know from our experience, depending on whether we extend or compress the spring will generate potential energy. It'll be quite difficult to keep that spring completely compressed. The spring wants to return to its resting state. Just like, for example, if you hold an object above the ground and you let go, the object will fall. Same principle. So a spring stores potential energy based on the position of each of the ends of the spring. Depending on where each of the ends of the spring are, the spring itself has stored a different amount of potential energy. And you can see this by the fact that when the ends of the spring are released, the spring will contract or expand to its lowest energy distance. So if we think about what's happening when we allow our spring to be released, the potential energy in the spring is being converted into kinetic energy. So for example, if we pulled our spring really far apart, so we have a high amount of potential energy. Actually, let's draw this as a separate picture. So let's suppose we have our spring. Okay, and initially it's fully extended. So we have a high potential energy. Now, if we're holding the spring, sure, we can keep the spring from moving back to its resting state. But if the moment we release the spring, what we'll immediately see is that both of the ends of the spring will begin to move closer together. And now my question to all of you is, what do we call this energy of motion? What do we call this energy of motion? If both ends of the spring are quickly moving towards each other with the velocity v, what has happened to our potential energy? What other form of energy are we now dealing with? We've taken our potential energy, the spring is initially, the ends are separated. We let go of our spring, the ends start to move. So what's happening to our potential energy? It's being converted into the energy of motion. And what do we call that energy? What do we call the energy of motion? Our potential energy, yes, exactly right. It is converted into kinetic energy. And then eventually you reach a point when the spring is at its resting state. And now the motion stops when the spring is at its resting state. If you're curious, well, wait a second, why is the spring stopping? Where'd that kinetic energy go? If we're being fully accurate here, some kinetic energy is lost as heat. Unfortunately, we're not in a vacuum, so things aren't perfectly frictionless. We do lose a little bit of energy to heat exchange, friction. Well, not lose, but energy is converted into heat. Okay, perfect. So we have this idea of potential energy. We looked at a spring, and now you may say, What does that have to do with chemistry? It's the spring. Well, if we think a little bit about charge-particle interactions, we can draw an analogy to the behavior of a spring. So we know for charge-particle interactions that like charges repel and opposite charges attract. Okay, perfect. Chemical bonds fundamentally involve the sharing of electrons between the nuclei of two atoms. So a chemical bond can be thought of as two positive charges sharing a set of negative charges. So we can think of and we can model chemical bonds very similar to modeling a spring. And in fact, this spring-like model is pretty common when discussing the spectroscopy associated with chemical bonds, looking at bond stretching and bending. So it's not outlandish to think about the same dynamics of kinetic and potential energy when you start looking and you start thinking about chemical bonds, their bond length, bond strength, etc. Okay, so let's show how we can apply this. Well, one of the main types of potential energy that we see in chemistry is known as chemical potential energy. So chemical bonds fundamentally involve the sharing of electrons between the nuclei of two atoms. So for example, a hydrogen-hydrogen bond can best be thought of as the two hydrogen nuclei sharing a pair of electrons. Okay, so looking at this picture, we can see very clearly that our electrons are stabilized by the nuclei of each atom participating in the bond. So we have this very stabilizing interaction between opposite charges. So in general, when you think of chemical bonds are stable. If we want to break this very stabilizing interaction between the electron and the nucleus, it's going to cost us some energy. So breaking chemical bonds costs energy, and forming chemical bonds releases energy. Okay? And that makes some logical sense. Bonds are stable. So if we're forming very stable, low energy bonds, some of that energy that was present in our starting materials gets released in the form of heat or other energy such as work. So the act of breaking high energy bonds and forming low energy bonds releases energy. So for example, one of the more societally relevant reactions that we've been trying to leverage, not necessarily unsuccessfully, but not as successfully as we would have hoped, is the combustion of hydrogen. So in this process, we are breaking hydrogen-hydrogen bonds and oxygen-oxygen bonds, and we are forming oxygen-hydrogen bonds. And the net to this reaction releases energy overall. One way that you can think about this, if you wanted to visualize this graphically, is that our hydrogen and oxygen are high in energy. As we run our reaction, we generate our water molecules, which have lower energy bonds. And as we convert our reactants to products, some of this energy is released in the form of heat. Okay. So we can use the combustion of hydrogen, for example, to generate heat to run an automobile engine, for example. So essentially, by looking at the relative energy of your starting materials and the bonds found in your starting materials to the bonds found in your product and the relative energy of your products, you can get a sense of how much chemical potential energy a sample has, how much potential energy, how much energy could be released when a substance reacts or undergoes a chemical change. So chemical potential energy is best defined as potential energy due to the chemical composition of a substance or mixture. Depending on its chemical identity, different samples and different materials have different chemical potential energies. So energy can be absorbed or released when a substance reacts to form new chemical compounds. Okay, so we'll come back on this idea in a little bit. For now, let's just introduce the next set of units that we're going to use in this chapter, which are units of energy. So the SI unit is the joule, has units of kilogram, meter squared per second squared. Okay. Another key conversion that you'll need to know is that 1,000 joules are equal to 1 kilojoule. Okay, that's a typical prefix conversion. If you happen to be in the English or imperial unit system, the other unit is the calorie. So 1 cal is 4.184 joules, and this is exact. A calorie is essentially the standardized amount of energy required to heat a gram of water 1 degree Celsius. The nutritional unit, so when you see the word calorie on the back of a bag of chips, for example, it is capital C calorie, and 1 capital C calorie is 1 kilocal, which is 4.184 kilojoules. So for example, if you see on your bag of chips, 250 calories per serving, what that is actually saying is that, well, if we have 250 calories, we know that we have 4.184 kilojoules per capital C cal, and we know that we have 10 to the third joules per kilojoule. And that in turn, this is just to give you an estimate of how many joules would a serving of chips have in terms of energy. 250 times 4.184 times 1,000, okay? So 250 cals times 4.184 times 10 to the third, that gives us 1.05 times 10 to the sixth joules of energy. Now, what does that mean? When we look on the back of the box and we see this value of the calories of a chip, for example, if we take, for example, our serving of chips or whatever, so let's suppose we take our serving of chips. Well, if we put our serving of chips into on a combustion setup, there's our serving of chips. And let's suppose we burn So if we burn our sample, that sample will in turn release heat. And if we completely combust our sample, if we completely burn our sample, we will generate about 1 times 10 to the 6 joules of energy released. It won't be perfect because there are some side processes occurring, but essentially all the foods that we eat and we handle on a day-to-day basis, when we eat them, we process them and we utilize some of the chemical potential energy found in the bonds and composition of food to generate energy that we can then use for a useful purpose, okay? So energy is best thought of as the capacity to do work, release heat, or affect chemical change. Does this make this idea of energy a little more tangible? Does it make a little bit more sense how energy functions and what each of these descriptions mean? Can I get some responses in the chat just to make sure everyone's comfortable with this idea? Okay, perfect. So let's talk next about a fundamental law of both physics, chemistry, and our universe, which is the law of conservation of energy. So the first law of thermodynamics states that energy cannot be created or destroyed. Energy can only be transformed from one form to another. So one of the common ways that we look at the energy of systems is the internal energy E. Internal energy is the sum of the potential and kinetic energy. So internal energy is equal to the kinetic energy plus the potential energy. Now, internal energy is known as a state function, and you're going to really like whenever it's said that something is a state function, because it allows you to be very creative and it allows you a lot of tools to solve problems very creatively. So what is a state function? Well, as the name implies, it's a property that depends only on the initial and final states of the system. So we only care about the initial and final states. So for example, if this is our initial energy and this is our final energy, it doesn't matter what intermediate steps we use to get there. It doesn't matter how we go from initial to final state. We can take this jagged path, we can take another path that goes through a slightly different series of steps. And the main key feature of a state function is that the path from initial to final state does not matter. Only the initial and final energies matter. We only care about our initial and final energy. It doesn't matter how we get there. And that allows us to use some really creative tricks to calculate the change in energy of different reactions. So state functions only depend on your initial and final states. We'll talk more about that in a bit. So another way of writing the first law of thermodynamics is that for an isolated system, the internal energy is constant. Now, we can't measure absolute internal energy, but we can measure changes in internal energy, or we can measure internal energy relative to an external standard. So thermodynamics focuses on changes in internal energy that we call delta E. Anytime you see the word changes, think the symbol delta. So if the internal energy of an isolated system is constant, then the change in internal energy would be zero. So delta E would be zero for an isolated system. Okay, so let's talk about state functions because we'll be seeing them a lot, and it's important to understand how state functions work in order to start to use state function properties to solve problems. So again, just to reiterate, we can't measure internal energy, but we can measure the changes in internal energy. Internal energy is also a state function. And as we discussed, a state function is a property that depends only on the initial and final states of the system, and it's independent of the path taken between the two steps. A system can undergo multiple steps with different changes in energy before reaching its final state. But all we care about is where we started and where we finished. That's it. Everything else doesn't matter. State functions overall often have the delta symbol in them. So let's look. So let's suppose we have an initial energy and a final energy. Again, just to reiterate, if we wanted to calculate delta E, or the change in internal energy, all we would do is we'd take E final minus E initial. We don't have to worry exactly about what path our system takes. It can be a really random path going through multiple different intermediates. That doesn't matter. The only thing that we care about is that we know the initial and final energy. The path doesn't matter. So just to help everyone grasp this idea, let's look at a practical example. So pretend you're driving to school, for example. You don't necessarily care about what road you take to your school. At the end of the day, if you're parked at the school campus, the distance from the school and your house is going to be the same. So let's just pretend we're looking at distance, and here's your initial position, and here is your final position at the school. It doesn't matter if you take a weird route where you go away from the school, then you go a little bit closer down a street, and you go through a series of turns, or if you take the freeway. Doesn't matter what path you take. At the end of the day, only your initial and final states matter. At the end of the day, if you check on your phone, how far away am I from my house? It'll say the same distance, or delta E is the same for each path. Does this idea of state functions make sense to everyone? Does the key feature of state functions make sense? They only depend on the initial and final states. The exact path doesn't matter. Okay, so now that we understand what the word state function means, let's now discuss the word heat. Unfortunately, the colloquial meaning of the word heat is often conflated with temperature. So heat and temperature are not the same. So the temperature of an object is proportional to the average kinetic energy of the particles. So temperature can be thought of as a proxy for the degree of molecular motion. So the higher the temperature, the greater amount of molecular motion. And at high temperatures, most molecules are moving at a higher average kinetic energy. So for example, if we look at a plot of kinetic energy versus number of particles with a certain kinetic energy, we can read from these plots, first and foremost, that the average kinetic energy is somewhere around the middle of the plot, of course, weighted. This one's a little tricky, but we'll just arbitrarily write that here. So we have our average kinetic energy. So as we see, for our high temperature sample, our particles on average have a higher kinetic energy compared to our low temperature sample. One other thing that you notice is that as we look at a high temperature versus a low temperature sample, the high temperature sample has a broader range of accessible kinetic energies. When we think about a collection of particles, the kinetic energy that we use to describe each of these particles is inherently going to be an average. Some particles are moving faster, some particles are moving slower than the average. But the key takeaway I want you to get from this, high temperature, higher kinetic energy, more molecular motion. Okay, so temperature is a proxy for the degree of molecular motion and the amount of molecular kinetic energy. Heat, quite simply, is energy, also called thermal energy, transferred between objects as the result of a difference in temperature, T, between objects. Heat is transferred between objects until they reach thermal equilibrium, until they reach the same temperature. Heat can be more simply thought of as the transfer of energy from regions of high temperature to regions of lower temperature. Now, one thing that's really interesting is that just like in our example when we said, oh, a fast-moving particle hits a slow-moving particle, they transfer energy, and suddenly the temperatures of those two samples change. Likewise, when substances absorb or release heat, the temperature of the sample will increase or decrease respectively. So heat has units of joules or calorie, and we've already discussed those units in detail. Does the distinction between heat and temperature make sense to everyone? Is everyone comfortable with the distinction between heat and temperature? Heat is energy exchanged between objects as the result of a temperature difference, while temperature is a proxy and a measure of the amount of molecular kinetic energy and the degree of molecular motion in your sample. Does this make sense to everyone? Any questions? Okay, so let's keep going now. And so heat is energy transferred between objects as a result of a difference in temperature, and heat is transferred between objects until they reach thermal equilibrium, until they reach the same temperature. So when heat is transferred from a high temperature object to a low temperature object, the high temperature object decreases in temperature and the low temperature object increases in temperature until both samples are at the same temperature. So just to make sure we understand conceptually what's going on here, so if we place a metal spoon at 25 degrees Celsius into boiling water at 100 degrees Celsius, what is going to happen to our spoon? So if we place our metal spoon into boiling water, what will happen to the temperature of our spoon? What will happen to the temperature of our spoon? Will it increase or decrease? Just intuitively. Yeah, it'll increase. And what's happening is heat is flowing from our high temperature boiling water to our low temperature spoon, and as a result, the spoon gains heat from the water, and as a result, the spoon increases in temperature. Okay, let's do another example. So if you place a metal block at 90 degrees Celsius into a container of ice water, what's going to happen to our metal block? And again, let's draw a picture. This time we have a metal block at 90 degrees Celsius, and we place that metal block into ice water at 0 degrees Celsius. What will happen to the temperature of our metal block? It'll decrease because our metal block loses heat, and in turn, the metal block decreases in temperature. So we're slowly starting to develop this method of tracking heat gained or lost by different components of our system. So now let's continue to focus on this idea of heat. But first, what we have to do is we have to define the ideas of the surroundings, the system, and our universe. So the system is the reaction or area under study. The surroundings, and yes, this is quite a liberal definition, is everything else. It's the rest of the universe. Another way to think about the surroundings, which is a little more nuanced, is everything that the system can exchange energy with. Now, there are three main types of systems. The first of which is known as an open system. And as the name implies, it can gain or lose mass and energy across their boundaries. So for example, if you have an evaporating dish that's filled with liquid, you can both exchange mass, you can lose liquid via evaporation, and you can also exchange heat. And we see this in our day-to-day lives by the fact that if you take an evaporating dish and you let it sit for a long period of time, the water will eventually evaporate. We are exchanging mass with our surroundings. You can also just as easily heat your evaporating dish and exchange heat with your surrounding. Now, the next type of system is known as a closed system. So closed systems can absorb or release energy, but not mass across the boundary. So a classic example of a closed system would be a light bulb. So thinking about the light bulb, first and foremost, we can touch, if you've ever done this as a kid, and when a light bulb's on, if you tried to touch the outer glass of the light bulb, you can see that heat can be exchanged. But mass cannot enter or leave the light bulb. Generally, the metal filament and other components inside the light bulb stay inside the light bulb. Does that make sense to everyone? So the light bulb can exchange heat. It can warm the air surrounding the light bulb. You can clearly touch the glass surrounding the light bulb and feel that it is warm. It's exchanging heat with the surroundings. But the light bulb, you aren't seeing the metal inside the light bulb leave the light bulb. Does that make sense to everyone? So the final type of system is known as an isolated system. And isolated systems cannot exchange matter or energy with their surroundings. I mean, there's no such thing as a perfectly isolated system, but one analogy that I would think of for an isolated system would be a closed thermos bottle. So if you have one of these really fancy, they're like inner vacuum sealed thermoses, they're pretty cool. So this is a vacuum. So it's completely air-free. So let's suppose you have your soup or lunch or whatever inside your closed thermos bottle. Well, if it's sealed, we know pretty easily that no mass can escape the container. And additionally, heat cannot be exchanged with our surroundings. So the vacuum, the real reason why a lot of these thermoses have this inner vacuum layer is that in this inner vacuum layer, there are very little, if not none, there are very few molecules or particles to transfer heat. Fundamentally, heat transfer requires a particle-to-particle collision. And if there aren't as many molecules or particles in this vacuum-sealed thermos, your heat transfer is going to be exceedingly inefficient. Does everyone understand these three types of systems? We'll be looking at each of them in the context of studying chemical reactions pretty soon. Okay, so let's look at some sign conventions for heat. How do we assign the sign of heat? So heat is transferred from regions of high temperature to low temperature until both regions have reached thermal equilibrium and are at the same temperature. So in terms of our sign conventions, if our system releases heat to the surroundings, then Q is less than 0. So Q is negative if we are releasing heat. If we're absorbing heat from the surroundings, Q is going to be greater than 0. So again, if we're absorbing heat, then Q is positive. Okay. We often look at energy changes measured from the point of view of the system. So endothermic systems, endo like endoskeleton inside. The system requires energy to be added, and the system absorbs heat. So Q is positive. Endothermic absorbs heat, Q is positive. Exothermic, like many insects have an exoskeleton, a skeleton on the outside. Exothermic reactions release energy to the surroundings. The system is releasing heat and Q is negative. Does this make sense to everyone so far? Okay. Now, a critical feature, just tying this back, we know that energy is conserved. So any heat lost by the system is gained by our surroundings. So then if we add up the heat exchanged by our system and surroundings, we will get 0, just with a little asterisk, assuming no work is exchanged. And we'll talk about what that means in a moment. That must seem like a bit of an odd sentence out of context. But essentially, if only heat is being exchanged, any heat lost by the system is gained by our surrounding, so our total net heat exchanged should be 0. Does that make sense? Energy is conserved. Any heat that's leaving our system must go somewhere, and it goes into our surroundings. Any questions on this example? Any questions on this idea? Okay, so let's keep going now and let's talk about heat capacity and heat transfer. What happens when samples absorb or release heat? Well, heat capacity is the extensive ability of an object with constant mass to absorb heat. Heat capacity depends on the sample mass and the chemical identity of the substance. So it depends on how much material you have and what is the chemical composition of that material. So heat capacity has units of joule per degree Celsius. And I'm going to need you to be very careful and pay attention to your units. So when a sample absorbs or releases heat, the sample's temperature changes. And what we can do is, although it's difficult to measure heat directly, by measuring the change in temperature of a sample as it absorbs or releases heat, we can calculate the exact amount of heat gained or lost by our sample. So heat can be calculated using the following equation, where Q is the heat transferred, C is the heat capacity of the object, and delta T is the change in temperature. So let's show an example of this. So let's suppose we're looking at an experiment where a cup of water has a heat capacity of 720 joule per degree Celsius. And we're asked, how much heat will it absorb if the experimental temperature is changed from 19.2 to 23.5 degrees Celsius? So using our equation, Q is equal to C times T final minus T initial. We know that our heat capacity, I'm getting ahead of myself here. It's 720 joule per degree Celsius. Okay, our T final is 23.5 degrees Celsius. Our T initial is 19.2 degrees Celsius. And that in turn, in order to change the temperature of our sample from 19.2 to 23.5 degrees Celsius, we would have to absorb, let's calculate that. So we have 720, 23.5 minus 19.2 times 720. We would have to absorb 3,096 joules, and we know that in 1 kilojoule we have 10 to the third joules. That gives us 3.0. We'll round this to 3 sig figs. That gives us 3.10 kilojoules. So we would need to absorb about 3 kilojoules of energy to change the temperature of our sample from 19.2 to 23.5 degrees Celsius. Does this example make sense to everyone? Does this example make sense on how to calculate heat absorbed or released by a sample based on the change in temperature and heat capacity of that sample? So to check that everyone's comfortable with these kinds of calculations, I'd like you now to attempt the following problem-solving session, and Canvas integration will be up later tonight for these problems. So let's work on the following example, and I'd like you to answer the question, what is the heat released by our sample of zinc? And don't be shy if you have any questions to unmute and ask your questions verbally, or to type your proposed responses in the chat. And make sure to include the right sign for the heat released by a sample by the sample. And the response I see in the chat looks good. Just make sure you're following the sign conventions. If we're releasing heat, make sure you have the proper sign to reflect that. And we'll discuss this example in about another 2 minutes. And the response I see in the chat with the sign looks perfect. Let's try to get a few more responses in the chat, or if you have a question, again, don't hesitate to ask it via the chat or unmute and ask your question verbally, and I'd be happy to get that addressed. And we'll discuss this example in about another minute. Okay, so let's discuss this example. Do we actually need to care about the mass of our sample in this case? Does the mass of our sample even remotely matter in this example? No, because we're given the heat capacity, and the heat capacity is directly related to the mass of your sample. So so the mass given is just needless information. So now we know the heat capacity, we know our initial and final temperature. So then we can calculate the heat released by our sample by taking our heat capacity, which is 0.387 joule per degree Celsius, times our final temperature, which is 22 degrees Celsius, minus our initial temperature of 100 degrees Celsius. And that gives us the heat exchange associated with our sample, 22 minus 100 times 0.387. That gives us a heat exchange of negative 30.2 joules. So we can say 30.2 joules of heat were released. So heat released, it's a negative sign. So just make sure you're respecting the sign conventions. Otherwise, your responses will be incorrect. Does this example make sense? The responses I saw in the chat looked perfect so far. Okay, so let's keep going now. Now, specific heat is a slightly different way of expressing how a sample can absorb or release heat and what happens to the sample when it absorbs or releases heat. So specific heat capacity, otherwise known as specific heat, it can either be written as CS or S. And specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat, really importantly, is independent of sample mass, but it depends on the chemical identity of your substance. The units primarily are joule per gram degree Celsius. You can calculate your heat capacity by taking the specific heat times the mass. So remember, the C with no subscript is the heat capacity. So suppose that you're heating a sample and you want to measure the heat required to change the temperature of a sample. You can calculate the heat by taking your specific heat, multiplying it by the change in temperature, and M is just the mass of your sample. So what this means practically is samples with a high specific heat resist temperature changes. Note that water has a very high specific heat. So I provided you a table of different substances and their specific heats. And we notice that most metals have pretty low specific heats. That makes sense intuitively. Metals pretty readily undergo changes in temperature when they absorb heat. Water, if you ever tried to boil water, it certainly takes a lot of heat to change the temperature of a sample of water. And of course, the more water you try to boil, the more heat required. Okay, so let's look at an example. I'll do this first one as a representative case. We're asked to calculate the specific heat of a metal if it takes 235 joules to raise the temperature of a 32.91 gram sample by 2.53 degrees Celsius. Okay, so we know that heat is equal to the mass times the specific heat times T final minus T initial, which is delta T. So we know in this equation, our delta T is 2.53 degrees Celsius, and it's positive because we're raising our temperature. Our heat is 235 joules. Our mass is 32.91 grams. So then, solving for the specific heat, we get Q over M delta T, which gives us 235 joules over 32.91 grams times 2.53 degrees Celsius. So punching that into our calculator, that in turn gives us a specific heat of 2.82 joule per gram degree Celsius. So we can use this information and equation to calculate any of these variables if we're given a set of known quantities. Does that make sense to everyone? So we have the tools available to calculate specific heat. Or in other words, to calculate the specific heat capacity.
What does it say on the bottom? 2.82.
A joule per gram degree Celsius. And that's actually one way of checking your work in these problems. If the units are correct, then likely you've performed your calculations correctly. And that's why I encourage everyone to utilize unit analysis and to just write out your units. So let's really apply this idea, and let's take a look and try to apply this concept to a new problem. I'd like you to calculate the specific heat of a liquid if it takes 222 joules to raise the temperature of a 24.1 gram sample from 25 to 27.3 degrees Celsius. So let's spend about 3 to 4 minutes on this example, and then we'll discuss momentarily. And again, don't be shy to message me with your proposed responses for this problem, as well as message me with any questions that you have, or you can unmute and ask your question verbally. So looking at the response I see in the chat, it looks perfect. The answer, if you're following the sign conventions, you will get a positive number for your specific heat. Specific heats are always positive. So the responses I see in the chat look great. For the long form response, just make sure that you're punching things into your calculator step by step, as you should get a number that is definitely going to be greater than 1. And we'll discuss this example in about another minute to a minute and a half. And if there are any other questions, we'll discuss this example momentarily. Okay, so let's discuss. So using our heat exchange equation, Q is equal to mCs times T final minus T initial. So substituting, we know that Q is 222 kilojoules, and it's positive. Our mass is 24.10 grams. Our T final is 27.3 degrees Celsius, and our T initial is 25.0 degrees Celsius. So solving for our specific heat, we have Q over M times T final minus T initial. So that gives us 222, whoops, that's not kilojoules. That would be quite the substance if that was the case. 222 joules over 24.10 grams times T final, which is 27.3 degrees Celsius, minus T initials, which is 25.0 degrees Celsius. So that in turn gives us a specific heat of 222 over 24.10 over 2.3. And that gives us a specific heat of 4.01 joule per gram degrees Celsius. Does this make sense to everyone? Does this response make sense? Is everyone comfortable utilizing this equation? Perfect. Okay. So let's look at another guided example. So this time we're asked to calculate the heat released when a 10-gram sample of lead at 63 degrees Celsius is placed in water and cools to a final temperature of 24 degrees Celsius. And then we're asked, what is the final temperature of the water sample? Don't worry, the second one, the second part, we don't actually have to do any math for. Okay, so Q is equal to mCs times T final minus T initial. Our T final is 24.0 degrees Celsius. Our T initial is 63.0 degrees Celsius. Our mass is 10.00 grams. And our specific heat, well, we can read that off from the table as 0.128 joule per gram degree Celsius. Now you may notice specific heats are listed at 25 degrees Celsius. Specific heats do depend on temperature, and they're best described as functions. But for this class, we're just going to assume the specific heat doesn't change too much with temperature. For all the engineers and chemists, this exact same topic will be covered in much more detail using more sophisticated math in upper division courses. So plugging into our equation, that gives us our heat exchanged by our sample equal to negative 49.9 joules. And we've done things correctly because this negative matches the idea that heat is released by our sample of lead. Okay, now this may seem like an odd question, but would anyone like to propose what is the final temperature of our water sample if the lead reached a final temperature of 24 degrees Celsius in the water sample? What would our final temperature of water be if the lead is at 24 degrees Celsius at the end of this process? What's the temperature of the water going to be if the water exchanged heat with lead? It's also going to be 24 degrees Celsius because remember, T final is the same for all samples in thermal contact. If the final temperature wasn't the same, they'd exchange heat until they eventually reach equilibrium. Does this example make sense to everyone? Any questions on this example? Okay, so let's try to apply what we've learned. Oh, why is it negative this time? Well, let's think about this from two perspectives. So first, intuitively, if you have like a really hot piece of metal, for example, and you drop it in water, what's going to happen to the metal? Is the metal is going to cool down and the water is going to warm up. So the reason why heat is negative is because heat is going out of our metal into our water. So if heat is leaving our sample, just like, for example, if you pay for something and you lose money, the value and the sign would be negative. Does that make sense? Perfect. So let's now look at another problem, and let's ask and try to calculate the heat released when a 15-gram sample of iron at 74 degrees Celsius is placed in water and cools to a final temperature of 22 degrees Celsius. And I'd also like you to tell me what is the final temperature of the water sample in this case. So let's spend about 3 minutes on this problem, 3 to 4 minutes, and then we'll discuss momentarily. Again, don't be shy to submit your proposed responses to me via the chat, to ask your questions via the chat, or to unmute and ask your questions verbally. Yep, and the response I see in the chat looks good. Just remember that the negative sign comes from the fact that T final minus T initial in this case should be negative. But otherwise, that response looks perfect in the chat. And we'll discuss this example in about another 1.5 to 2 minutes. And let's try to get a few more responses in the chat. Okay, so let's discuss this example. So the heat released by our sample of iron is equal to the mass of iron times the specific heat times T final minus T initial. So substituting, we have 15.00 grams. The specific heat of iron is 0.4498 joule per gram degrees Celsius. T final is 22 degrees Celsius. T initial is 74 degrees Celsius. So punching this into our calculator, that in turn gives us 22 minus 74 times 0.4498 times 15. That in turn gives us negative 351 joules. So this is how much heat is released by our sample of metal into our water. And we know that the T final of water is the exact same of our metal, which is 22 degrees Celsius. Any questions on these examples? Any questions on these examples? Okay, so let's look and let's try to explain heat transfer between objects. And to do that, we're going to apply the first law of thermodynamics, which states for an isolated system, the internal energy is constant. So another way of phrasing the first law of thermodynamics is that the sum of all heat transfers of all materials and all work processes of a system will be 0. Okay. Now we know that objects at different temperatures will exchange heat until thermal equilibrium is reached, and that the final temperature is the same for all materials in thermal contact. Okay, so first and foremost, any heat released by the system is absorbed by the surroundings. So for example, if this is our system and everything around our system is our surroundings, if heat is leaving our system, we know that the Q system is less than 0. And since the surroundings are gaining heat, we know that Q surroundings are going to be greater than 0. Since the same amount of heat, since energy must be conserved, the same amount of heat lost by our system must be gained by our surroundings. So Q system is equal to -1 times Q surroundings. To look at the converse example, any heat absorbed by the system must be released by the surroundings. So for example, if we have our system, and this time our system is absorbing heat from our surroundings, so it's engaging in an endothermic process. We know that Q system in this case is greater than 0, so Q surroundings going to be less than 0, as our surroundings are releasing heat into our system. Again, as always, Q system is going to be equal to -1 times Q surroundings. If energy is conserved, any heat lost by our surroundings is gained by our system. Okay, so let's keep going with this concept. If we know that the total energy of an isolated system remains constant, if we add up all of our heat gained and lost by our system and surroundings, we should get 0. Solving this expression, we see that the heat exchanged by our system is equal to -1 times the heat exchanged by our surroundings. Note, an isolated system is a system that cannot transfer heat or material with any components outside of that system. Okay, now you may ask, how do we measure the heat gained or lost by our system or surroundings? Well, we can measure the heat gained or lost by the system by measuring the change in temperature for that system. So Q is equal to mc delta T, okay, just like before. Likewise, we can measure the heat gained or lost by the surroundings by measuring the change in temperature of our surroundings. So Q is mc delta T. Wonderful. Now, if Q systems is -1 times Q surrounding, if we substitute in, we see that our expression for Q system is equal to -1 times our expression for Q surroundings. So by measuring the change in temperature of our system and the change in temperature of our surroundings, we can in turn calculate and determine the mass or the specific heat of any component of our system and surroundings. So given certain quantities, we'll be solving this equation to figure out unknown quantities. Now, let's look at a common example of how we can apply this idea of heat transfer and how we can model heat transfer in order to calculate the heat exchanged between our system and our surroundings. Okay, so let's read through this problem. A 43.29 gram sample of solid is transferred from boiling water to 152 grams of water at 22.5 degrees Celsius. The water temperature rose to 24.3 degrees Celsius, and we're asked to calculate the specific heat of the solid. Okay, so I like to draw pictures here. Okay, so we have our solid. So the mass is 43.29 grams. The temperature initially is 99.8 degrees Celsius. Okay. And surrounding our sample is water, which has a mass of 152 grams and an initial temperature of 22.5 degrees Celsius. Okay, so as the metal block is at a higher temperature, I'm just going to arbitrarily designate the solid as our system. So what surroundings is our solid exchanging heat with? So what is surrounding our solid? What is our solid exchanging energy, exchanging heat with? What is our solid exchanging heat with? What is gaining any heat released by our solid? And don't be shy to type it in the chat. So what is our solid exchanging heat with? What is our solid transferring heat with? What do we place our solid into? What is our solid exchanging heat with? What is warming up as a result of putting our solid into water? What is gaining that heat? Water, exactly. So we're going to designate the water as our surroundings. It is the principal component that is exchanging heat with our system. Okay, so now that we have our systems and surroundings defined, our solids at a higher temperature, so it's going to release heat into our surroundings. So we know that Q solid is going to be less than 0 and Q water is going to be greater than 0. And we know that Q solid is equal to -1 times Q water via conservation of energy. Okay, we know that at the end of this process, eventually we'll have our solid and our water at the same temperature. In this case, what is our final temperature of both the solid and the water? So what is the final temperature going to be? Oh, I mean, just looking in the problem, what is our final temperature? 24.3 degrees Celsius. So the final temperature is going to be the same for both our solid and our water sample. So now what we're going to do is we're going to look at and expand out our initial expression. So we know that the mass of our solid times the specific heat of our solid times T final minus T initial is equal to -1 times the mass of our water, which is our surroundings, times the specific heat of water times the change in temperature of water. Now what we're going to do is we're going to substitute. The mass of our solid is 43.29 grams. The specific heat of our solid we don't know. So before we substitute, let's solve for the specific heat of our solid. So the specific heat of our solid gives us -1 times the mass of water times the specific heat of water times T final minus T initial for water over the mass of solid times the specific heat of our solid. Oh, sorry, over the mass of our solid times T final minus T initial for our solid. So now that we have this expression in place, we're going to solve and plug in what we know. So we know the mass of water is 152 grams. The specific heat of water is 4.184 joule per gram degree Celsius. The T final of water is 24.3 degrees Celsius. The T initial of water is 22.5. We're just reading off all the data that we know. The mass of our solid, let's go find the mass of our solid, is 43.29. The T final is 24.3 degrees Celsius, and the initial temperature is 99.8 degrees Celsius. So punching this into our calculator, we get 152 times 4.184 times 1.8 over 43.29 over 75.5. And that in turn gives us a specific heat of 0.350 joule per gram degree Celsius. Does this example make sense to everyone? Notice how if I punch in my numbers correctly, I get a positive specific heat. If for some reason you get a negative specific heat, you've likely made an error in your calculations. Does this example make sense? I really encourage you, especially at the start for thermochemistry, draw a picture. What things are exchanging heat? What do I know? And then once you have that clearly defined, you can more effectively use your equation. Does this example make sense? Any questions in the chat? Okay, so let's try to apply what we know, and let's look at the following example. And I'd like you to calculate the specific heat of a solid given the following information. And we'll discuss this example momentarily. And if you have any questions, don't be shy to unmute and ask your questions verbally. And we'll discuss this example in about 3 to 4 minutes. And the response I see in the chat in equation form looks good. Just remember to enter the entire bottom portion of your calculation in one set of parentheses, just to avoid calculator errors. And we'll discuss this example in another 2 to 3 minutes. And let me check the response in the chat. Oh, make sure to account for the specific heat of water. And remember, just as we discussed earlier, the specific heat of water is 4.184 joule per gram degrees Celsius. So take a moment to revise your calculations, and we'll discuss this example in about another 2 minutes. Yep, and the setup looks good. The setup I see in the chat looks great. And if anyone else has any questions, or if anyone would like to provide their proposed responses, don't be shy to type out your proposed responses in the chat so I can provide feedback. Yep, and the response I see in the chat looks great so far. So let's discuss. First, let's make a picture. Let's make a picture. That is often the best way to check to make sure that your sign conventions are correct. Okay, so we have our sample and we have the water. Okay, so we know that the mass of water is 122.6 grams. The specific heat of water is 4.184 joule per gram degrees Celsius. The T initial of water is 10.5 degrees Celsius, and the T final is 11.2 degrees Celsius. Okay, now let's look at our sample. The mass of our solid is 10.5 grams. The specific heat of our solid, well, that's what we're trying to figure out, of course. The T initial of our solid is 99.8 degrees Celsius, and the T final of our solid is 11.2 degrees Celsius. Okay, so now we know that Q solid is equal to -1 times Q water. In other words, the mass of our solid times the specific heat of our solid times T final minus T initial of our solid is equal to -1 times the mass of water times the specific heat of water times T final minus T initial of water. Okay, now solving this expression, the specific heat of our solid then turns into -1 times the mass of water times the specific heat of water times T final minus T initial of water over the mass of solid times T final minus T initial of solid. Okay, that in turn gives us, for our specific heat of our solid, we have -1 times 10.5 grams times, oh, whoops, sorry, I need to use the mass of water, which is 122.6. The specific heat of water is 4.184 joule per gram degrees Celsius. Our T final is 11.2 degrees Celsius. Our initial temperature of water is 10.5 degrees Celsius. Dividing by the mass of solid, which is 10.5 grams of solid, the T final of our solid is 11.2 degrees Celsius, and the T initial is 99.8 degrees Celsius. Punching this into our calculator for the specific heat, we get 0.386 joule per gram degrees Celsius. And notice how if we enter everything properly into this equation, we get a positive number. Does that make sense to everyone? So with that said, we'll pause today's lecture and we'll take a short break and then resume for laboratory at 12:45.